Hello everyone, my name is Jyotirmoy and me and my team will be explaining the Cauchy-Riemann equations. The Cauchy-Riemann equations use the partial derivatives of u and v to do two things. First, to check if a function has a complex derivative, and second, to compute that derivative. We will start by expressing the equations as a theorem.
Hi, my name is Anurup Biswas. So if there is a f of z is equal to is analytical and f dash z is equal to, in particular, del u by del x is equal to del v by del y, and del u by del y is equal to del v by del x. So these partial differential equations, above equations, are usually meant by the Cauchy-Riemann equations, and here is the short form the Cauchy-Riemann equation. Ux is equal to vy is so uy is equal to minus vx.
So let's dive into the proof.
Suppose that f of z is differentiable and in some region A, and we will compute f dash z by approaching z first from the horizontal direction and then the vertical direction. Now we will use the formula.
Theorem 2.
Consider the function f of z equal to u of xy plus iv of xy defined on a region A. If u and v satisfy the Cauchy-Riemann equations and have continuous partials, then f of z is differentiable on A. Let's dive into the proof. The proof of this is a tricky exercise in analysis. It is somehow beyond the scope of this class, so we'll skip it. If you were interested, with a little effort you should be able to grasp it.
Let's talk about another theorem. If f of z is differentiable on a disk and f dash z is equal to 0 on the disk, then fz is a constant. The proof for this is, since f is differentiable and f dash z is almost equal to 0, the Cauchy-Riemann equations show that we know from multivariable calculus that a function of x comma y with both partials identically 0 is constant. Thus, u and v are constant, and therefore so is f.
Okay, so let's consider an example. Use the Cauchy-Riemann equation to show the Ez is differentiable and its derivative is Ez. So, solution, we write so and computing partial derivatives, we see that uz equals to uy and uy equals to minus uz, so that Cauchy-Riemann equations are satisfied. Thus, Ez is differentiable and
Let's consider another example. Use the Cauchy-Riemann equations to show that f of z equal to g bar is not differentiable. So here is the solution. F of x plus iy equal to x minus iy. So e of x comma y equal to x comma v of x comma y equal to minus y. Taking partial derivatives, ux equal to 1, uy equal to 0, vx equal to 0 and vy equal to minus 1. Since ux is not equal to vy, the Cauchy-Riemann equations are not satisfied and therefore f is not differentiable.
Expression of the Cauchy-Riemann equations. The central message of the Cauchy-Riemann equations is that when dealing with analytic functions, the real and imaginary parts of complex numbers cannot be regarded as independent quantities, but are closely intertwined. Consequences of the Cauchy-Riemann equations. Often, the easiest way to prove that a function is analytic in a given domain is to prove that the Cauchy-Riemann equations are satisfied.
More generally, we can use the Cauchy-Riemann equations to prove the following facts about analytic functions. Number 1. Compositions of analytic functions are analytic. Number 2. Reciprocals of analytic functions are analytic except at singularities.